So let's talk about the numerals that are base 10. Those are the ones we're used to. So each natural number can be written as a sum of powers of 10. And that's what we use to be able to write those using base 10 numerals. So here's the number 174, okay? 174. I'm thinking of that actually as the number 174. And the way that we write it like this is we say, well, that's 4 times 10 to the 0. That's the 4, right? And plus 7 times 10 to the 1, okay, that's the 7, plus 1 times 10 to the 2, or 10 squared. And notice that this is positional, right? So that the rightmost position is how many 10 to the 0s do I have. The one immediately to the left is how many 10 to the 1s I have, and so on. This is the reason that we actually need the numeral 0, right? You know, I told you it was one of the great discoveries of humankind. And here's why. Because if I want to have 1,074, okay, then I can actually do that. But now what I have is 4 times 10 to the 0s, 7 times 10 to the 1s, and 0 times 10 to the 2, okay? And then 1 times 10 to the 3. If I didn't have the concept here, 0 here, right, so if that wasn't there, then I couldn't tell those numbers apart, 174 and 1,074. And that's the problem that the ancients had. And before they invented 0, that's why they couldn't have really a nice notation for this that makes addition and multiplication and all those operations easy. Okay, so yeah, that's why 0 counts. Okay, now an important property of this representation is that it's unique. Okay, except for leading zeros, right? So I can put a leading 0, 2 leading zeros, 5 leading zeros, and that doesn't change the number. But if I ignore the leading zeros, then what I'm left with is a unique representation, a unique sequence of numerals, right, for a particular number. Okay, so there's no other way to write 174. Again, assuming that we don't count leading zeros. So starting with the 1, there's no other way to write 174. There's no other way to write 1,074. Okay, and that's pretty cool. Okay, that's an important statement. So let's actually make that statement, right? Let's prove it. So what we have is that n is equal to this sum, which is a sub I times 10 to the I, okay? And an a sub I is a natural number that's between 0 and 9 inclusive, or 0 and 10, but not including the 10, okay? So what we're going to claim is that n is actually equal to 0 if and only if all of the a sub I are equal to 0, right? So if any of these a sub I happens to be, for example, right, let's say that that one of them is 5, okay? So 5 is equal to a sub 3. Okay, then the number can't be 0. Okay, well, so how do we prove something like this? The first thing is just to say, well, duh. Okay, and that works sometimes. You know, proof by intimidation. It's obvious, right? And if you don't get it, then that's the intimidation part. But and the reason that is really painfully obvious, right, is that if any digit is not equal to 0, then we're going to be adding that digit times 10 to the something, right? And so that's a positive number, and we're adding a whole bunch of things, and all of them are positive or 0. So once I have something that's positive, there's no way to get back to 0 because I don't have any way to subtract, right? You know, each digit adds something. So yeah, it's clearly true. Okay, I want to actually take a second proof, and the reason is that this is, although it looks like a trivial theorem, is actually a really important theorem. And that's because I want to show that this representation is unique. Remember that? You know, the representation base 10 is actually unique up to leading zeros. And one thing that you'll see if you do any kind of advanced math is that whenever you want something to be unique, you actually have to say something about the values that are 0. Okay, and there has to be only one. So, for example, when you solve differential equations, okay, then the way that we solve them is we come up with the unique part, and then we add all of the things that can map to 0. Okay, that's the form that all those solutions take, and the solution is unique if there's only one thing that can map to 0. Okay, so anyway, so let's actually go ahead and try to continue this proof. Okay, so what we have is that n, right, is equal to some sum from I equals 0 to n of a sub I times 10 to the I. Okay, so we'll prove this. Let's see, what should we use to prove this? How about induction? Okay, you know, that's our main proof technique, and it's going to work beautifully here because our base case is going to be n is equal to 0. Okay, so what we have is that the sum from I equals 0 to n of a sub I times 10 to the I is actually going to be equal to the sum from I equals 0 to 0 of a sub I times 10 to the I, and that's actually just equal to 0 times, a sub I times 10 to the 0, right, which is just equal to a sub I. Okay, so what we have is that since capital N is equal to this, n is equal to 0 must imply that a sub I is equal to 0, right, because the sum is actually a sub I. So yes, right, that's exactly what we wanted to show. Okay, so now let's do the induction step. Okay, so our induction step is going to look like this. N is equal to the sum from I equals 0 to n plus 1 of a sub I times 10 to the I. Okay, and what I'm going to do is I'm going to try to break that up into two pieces. Okay, so the first piece that I want to have is when I is equal to 0. So I just want this to be a sub I, actually a sub 0, right, times 10 to the 0, okay, plus the sum from I equals 1 to n plus 1 of a sub I times 10 to the I. Okay, and now I'll take this part here. Well, this part here is just a sub 0, okay, plus, and then this part here, and what I'll do is I'll take one of the 10s, right, and take it outside of the sum. So I have this is 10 times the sum from I equals 1 to n plus 1 of a sub I 10 to the I minus 1. Okay, so I just pull one of those 10s out. And actually, you know, that's the same as a naught plus 10 times the sum from I equals 0 to n, right, of a sub I. And now I don't want a sub I. What I need is a sub I plus 1, right, because it goes from a1 to n plus 1. So since my index goes from 0 to n, I need I plus 1 times 10 to the I. And actually 10 to the I is correct because I had 10 to the 1 minus 1 up to n minus 1. Okay, so now I ask you to take a look at this. Okay, and what I want you to see is that actually matches the term that I started up with. Okay, so you know, I can kind of use the induction hypothesis here, right? Almost. But first what I have to do is, like, you know, with the induction tells me that if n is equal to 0, right, then all the a sub I have to be 0. Okay, now why should this sum end up being 0? Okay, well, what I know is that capital N is equal to 0. Okay, I also know that a naught is either 0, 1, 2, all the way up to 9. Okay, that's what I know about a naught. Okay, and then this, whatever it is, let's call it n1. Okay, it's just sum, right, is multiplied by 10. Okay, so this term, the second term, right, 10 times n1 is equal to, well, it could be 0, right? You know, that's one possibility. Or it could be 10, or it could be 20, or it could be 30, and so on. Okay. All right, so now a naught plus 10 times n1 is equal to 0 because that's equal to n, right? So that's supposed to be equal to 0. So how can I make this equal to 0? Well, if a naught is equal to 2, for example, right, there's no way to make this end up being minus 2. Okay, because it's 10 times something. It's 10, 20, 30, 40. So a naught has to be 0. Okay, so a naught has to be 0. Otherwise, you know, the 10 times thing is honestly too big to be able to cancel it. Okay, so yeah, so we have that a naught is 0. So now what I have is that n is equal to 10 times n1. N is 0. So 10 times n1 has to be 0. Well, that means that n1 has to be 0. Okay, so what we've shown here is that n1 has to be 0. Okay, now let's think for a second about what that means. What that means is that n1, which is the sum from n equals 0 to n of a sub I minus 1, okay, times 10 to the I, this is n1, is equal to this, is also equal to 0. Okay, so now by the induction hypothesis, goodness, I can write. So by the induction hypothesis, all of the a sub I, I'll write it as a sub I minus 1 to be clear, right? But all of those a sub I must be 0. Okay, so what have I shown, right? So a naught is equal to 0. Remember, we showed that because if it was anything else, then that number plus 10 times a natural number, there's no way that would cancel out, right? So for example, if it was 3, 10 times some natural number would have to be minus 3. No, that can't happen. So A naught has to be 0. I also now know that A1 is equal to A2 is equal to all the way up to n, A sub n. Okay, those also must be 0. Okay, so that's there you have it. Okay, so if that entire numeral is equal to 0, then all of the digits in that numeral must be equal to 0.